In this section 11-2, we will consider only objects that roll smoothly along a surface. No bouncing or skidding or slipping. So let's look at the example of a wheel rolling across the floor, and we'll pick a point on the outside rim. And as it rolls, we see that it forms quite a complex curve. The center of mass, where the axis of rotation is, follows a nice straight line, but a point on the outside edge creates what's called a cycloid, which is a bit of a complicated thing to study. What we'll do is we will look at rolling motion as a combination of purely rotational motion happening while purely translational motion is happening at the same time. Let's start by measuring the diameter of our wheel. Looks like 61.5 centimeters. I've put a mark on the wheel that marks a spot on the outside edge, and along the edge of the countertop here I've taped a tape measure, so I can measure in centimeters the distance the wheel moves in one complete rotation. So I've lined up my mark at the 0 spot, and of course that is in line also with the center of mass of the wheel. And now I'm going to roll it through one rotation, and I'm going to follow this mark through one complete rotation, and when it gets over here, I'm going to look at my tape measure and read that it came to the 193 centimeter mark. So remember, the diameter of the wheel was 0.615, so that means the radius is going to be half that. And we just measured that the wheel rolled along the counter 193 centimeters. So that is the distance the center of mass traveled. But it's also the arc length of the rotational motion. So that's S. So we saw that the wheel moved across the counter 1.93 meters. That is the distance the center of mass moved of the wheel from this position to this position. We'll call that linear motion x. So x equals 1.93 meters. I also know that if I were to put paint along the edge of that wheel and roll it across the ground, it would leave a line of paint on the ground, and after one rotation, that line of paint would be 1.93 meters. That is the arc length subtended by the rotation of the disc. So this is also equal to arc length S. We can double check that the arc length S is equal to the distance traveled by using S equals R theta, and we know we measured the radius of the bike tire. We measured the radius of the bike tire to be 0.308, and the angle that the wheel rolls through during one rotation is 2 pi. And when I get my calculator and punch it in, .93, which matches the distance that I measured, the linear distance that I measured. So it checks. So my position is x, my arc length is s, and I know when I take the derivative of position with respect to time, that gives me linear velocity. So that is the velocity of the center of mass of the wheel. And if I take the time derivative of arc length, that tells me the tangential velocity of the wheel. Both x and s are both 1.93 meters. The time it took for each of those is the same. So that tells me that the velocity of the center of mass of the wheel is the same as the tangential velocity of the wheel. And we also know from relating the linear variables to the angular variables that the tangential velocity is equal to radius times angular velocity. So here's what we've got so far. We know that S is equal to r theta, and we just showed that the velocity of the center of mass is the same value as the tangential velocity at the edge of the wheel. And of course that is equal to r times omega. We can think of rolling motion as being both rotational motion happening at the same time that translational motion is happening. If we combine this motion with this motion, we get this motion. Here we see pure rotation, and the vectors represent the tangential velocity at the edge of the wheel, which we know is the same as the velocity of the center of the mass of the wheel when we're in translational motion. Here the vectors represent just the translational motion of the wheel. So here are two diagrams that represent what we just saw. The first one was pure rotation, and the velocity at the top of the wheel is to the right, the velocity at the bottom of the wheel is to the left. In other words, there is a clockwise rotation of the wheel, and the tangential velocity is equal to the velocity of the center of mass when the wheel is rolling along the ground, and the translational motion, we'll call that VCOM, the velocity of the center of mass. And just looking at the translational portion of it, all parts of the wheel are moving at VCOM. When you combine these two, of course, rotation and translation are happening at the same time. So at any moment, the velocity at those points on the wheel is the sum of those vectors. So this vector plus this vector gives us 0. That means where the wheel is in contact with the ground, there is 0 velocity. And that is true because if you think about it, if the wheel had some velocity with respect to the ground, it would not be stuck to the ground. It would be sliding or slipping. The fact that the wheel is in contact with the ground and there is no sliding or slipping tells us that that point of the wheel has 0 relative motion to the ground. In other words, it is not moving, just for a brief moment. Over here, there is no velocity of the center of the wheel, so there is only the translational portion of it at the center. The center of the wheel is moving at VCOM. And at the top part of the wheel, we see that there's the tangential velocity plus the translational velocity for a total velocity of twice the velocity of the center of mass. Yes, the top part of the wheel is moving with respect to the ground to the right at twice the speed that the axis is moving. And let's look at a picture to demonstrate this. Here in this picture, even though it's moving to the left, where in my other diagram it was moving to the right, you can still see that at the bottom, the velocity of the wheel with respect to the ground at that point of contact is 0. The axis is moving at the velocity of center of mass, and the top is moving at twice the velocity of the center of mass. And this picture demonstrates this nicely because you can see up here at the top, the spokes are blurry and out of focus, whereas here at the bottom, they are sharp and in focus. That's because we know that when you try and take a picture of a moving object, oftentimes it is blurry. So that's what we see up here. Because the spokes are moving twice the speed of the center of mass, they are blurry. At the middle, things are in fairly good focus, and at the bottom, they're in very sharp focus. So that's what we got when we looked at it as combining pure rotation with pure translation to come up with rolling motion. There is another way of looking at it, however. We could consider it rolling as pure rotation, where the wheel at any given moment is rotating about a point that is not at point O, but rather at a point where the tire is in contact with the ground. And at any given moment, the tire is rotating about that point. And if we look at it in this diagram, we see that for various points on the wheel, there is a circle that is moving with center at this point where it is in contact with the ground, and the velocity at all those points are tangent to the circle. This velocity is tangent to the blue circle, this velocity is tangent to the red circle, this velocity tangent to the orange circle, and this velocity tangent to the black circle, and all the circles are concentric, having their center at the point at which the tire is in contact with the ground. We can show this vectorially in the same way that we added vectors before. Before we only did it at the bottom and the top. Now let's do it at all those different points. We're going to add the tangential velocity shown in red with the translational velocity shown in blue. We'll add them with the parallelogram method of vector addition, where you draw the vectors tail to tail, formulate a parallelogram with the vectors, and the sum of the vectors is the diagonal of the parallelogram. And we see that in all these cases, the sum of the vectors does match our diagram here, showing that the velocity is increasing in magnitude until it's twice the velocity of the center of mass at the top, and then decreasing in magnitude back to a velocity of 0 at the bottom. And of course, the direction of the velocity is also changing. In this short movie of a person riding a bike that has two different size wheels, try to answer these questions. Is the tangential velocity at the top of the large wheel the same, more, or less than that at the top of the small wheel? And also ask yourself, how do the angular velocities of the large and small wheel compare? To answer this question, we look at diagram C here and notice that for any size wheel, the tangential velocity at the top of the wheel is equal to twice the velocity of the center of mass. So for this bicycle, both wheels are moving across the ground at the same speed. So they both have the same VCOM. So therefore, they both have the same tangential velocity at the top of the wheel. To answer the second question, the angular velocities, how do they compare? VCOM for each wheel is equal to the radius of the wheel times its angular velocity. And since VCOM is the same for both wheels, this statement here is true. And if we rearrange this statement, we come up with this proportionality statement. And if the radius of the big wheel is bigger than the radius of the small wheel, then omega 2 must be a bigger number than omega 1. Or, since the large wheel has a larger circumference, it doesn't have to rotate as fast to go the same distance.